So I'd like to start by thanking FreeMind for hosting this great event and inviting us to speak. If you take away one thing from my talk today, I want it to be an understanding that increasing mitophagy can conquer many diseases. So our journey in drug discovery probably looks familiar to a lot of you, where you start with an idea and you develop through development candidate to the clinic, and ultimately one day we hope to therapeutics that can help patients. And throughout this path, there are many diverse funding opportunities, some sources that you can leverage. At the earliest stages, particularly grants are a big part of this. The other area are investors, but I think particularly you have to focus on mission-aligned investors, particularly angel investors are a good source here, who really want to see what you're developing make it into human use. As you start to get closer to the clinic and moving through toward products, then you have a good thing that you can take to institutional VCs, maybe start to partner with pharmas, and ultimately public market investors. So non-dilutive funding has been a big part of our strategy at Vincere. We have multiple grants, over $2.7 million in our first few years of life as a company, from multiple NIH institutes, as well as the Michael J. Fox Foundation. FreeMind Group has, of course, been very helpful in accelerating our pace of submission on this. As you all know, the funding rates on grants are 15 to 20%, maybe, right? And so if you want to get funded, you have to put in a lot of them, and they have to be very high quality. The other area of non-dilutive funding that I would encourage everybody to think about are pharmas. We've had cash and in-kind support from Johnson & Johnson and Bristol Myers Squibb, including funding our bench space at Lab Central in Kendall Square. So those are great opportunities that, in both cases, with these grants, give you not just cash, but also some great feedback from opinion leaders in the field, and can also help to kind of build the relationships early that will give you partnerships down the road. So I want to talk a little bit about the work that we do at Vincere. We know that damaged mitochondria lead to age-related decline in many contexts. There are a lot of things that can cause mitochondrial damage, and when this happens, your cells normally are able to package those up for recycling through mitophagy, and when that doesn't happen, you get reactive oxygen species, inflammation, and other things that lead to aging and cell death. So we've developed molecules now that can accelerate this process of mitophagy and bring the cells and tissue back to a healthy state. This is particularly important for Parkinson's disease, where there are 4 key lines of evidence that tell us this is a good therapeutic strategy. First and foremost, human genetics, about half of the mutations that cause Parkinson's are directly in this mitophagy pathway. When you look at tissues from sporadic Parkinson's, again, you see markers of deficient mitophagy. And then in animal models, if you increase mitophagy, you can protect in the model of disease. And in our computer simulations of human tissues, we also see that increasing mitophagy is protective. Mitochondria being the powerhouse of the cell in all of your tissues everywhere, it's maybe not surprising that this has application to other energetically demanding tissues. And one we're particularly interested in is acute kidney injury, which provides potentially a faster path to human proof of concept. And here again, there are a lot of ways you can damage your kidneys. And when you do, if the tissue has sufficient levels of mitophagy, then you recover and go back to normal health. But if that mitophagy process is deficient, then you progress through damage and to kidney failure. Beyond Parkinson's, AKI itself is a fairly large market, 10 million hospitalizations in the US each year and growing rapidly. So with all of that evidence, we've now developed small molecules that can increase this mitophagy process. When there's mitochondrial damage, which is indicated here with the dotted line, from something like CCCP as a toxin, the cells naturally increase this process. But if you apply our molecule, then you get a really robust dose-dependent increase on top of that. If there's not mitochondrial damage, the molecules are relatively inert, which we think is a great safety signal for these molecules. They're not just rampantly clearing mitochondria, they're preferentially clearing damaged mitochondria. In vivo, we've been able to measure mitophagy as well using two really cool new transgenic mouse lines, MitoQC and MT-Chema. Both of these have fluorescent mitochondria that are green normally and then flip to red when they go inside the acidic lysosome. So using this, we've demonstrated that our molecules get into the brains of mice and increase mitophagy in the brains of mice. The amount of mitophagy that we see with our molecules is very similar to what David Simon's group at Harvard published just last month in Nature Communications. And that level of mitophagy was able to protect in an alpha-synuclein model of Parkinson's disease. On the left with neurodegeneration, loss of Th-positive neurons, and on the right with alpha-synuclein pathology. So this was a really nice validation of the approach for Parkinson's that was using USP30 knockout, and our molecules selectively inhibit USP30. With kidney, there have been a lot of literature publications showing that deficient mitophagy is deleterious, but none showing that increased mitophagy is protective. So we're excited to have our own data, as of yet unpublished, but hopefully we'll get out sometime soon, showing that our molecules are protective here in a rhabdomyolysis model of injury, where you see increased blood biomarkers of BUN and creatinine, as well as kidney changes with KIM1 and histopathology, all of which are higher in the disease state and then reduced when you treat with our molecule. This was pre-treatment, but we also wanted to show that our molecules could accelerate recovery if given after the injury, which is more clinically likely scenario. So here you see on the x-axis days since injury, and then those same blood biomarkers of injury. On day one, you get large injury in both of those in the red line, and then right after taking that blood point, we treated with our molecule, and you see a greatly accelerated recovery with our molecule. Looking at a more chronic model of kidney injury, here dosing with cisplatin, which is a common chemotherapy agent, which is known to accelerate aging and cause kidney damage, as seen here with the increasing BUN levels. If you treat with our molecule weekly, just after each of the cisplatin treatments, we're able to keep those kidney levels at a normal functioning state. So we think all of that gives us a great rationale to take this forward for kidney injury, as well as with Parkinson's disease. So having protection from one mechanism in the brain and the kidney, we get a lot of surprise on that, why we're looking at two different therapeutic areas as one company. But I think the key here is dysfunctional mitochondria is a hallmark of aging. So it's maybe not surprising that you see everything start to go wrong and that this mechanism can be broadly protective. And indeed, in the literature, you can see if you increase mitophagy at the top through overexpression of parkin, and at the bottom through urolithin A, which is a molecule purported to increase mitophagy, you can extend lifespan of flies and mice. We're also happy to see a growing amount of evidence for this target within the field. When we prioritized the target, there were 20 publications in the world naming USP30 at all. And these 6 publications came out in the last quarter showing USP30 involvement in a variety of diseases, from Alzheimer's to brain injury to muscle failure. So excited to have now well-optimized molecules ready to go into the clinic. We have 2 classes of molecules, some that are brain penetrant and optimizing towards CNS indications, as well as others that are peripherally restricted that would be good candidates for cardiorenal and others, and then a few other programs behind that. So overall, we have this great momentum now leading into the clinic. We've had great support from the granting agencies as well as early stage investors, including Freemind Investments, who have been helpful in both funding and helping with some other introductions. And we stand now ready to go into the clinic with a really exciting new mechanism. With that, I'd like to acknowledge our growing Boston team of scientists that are doing some of the basic biology work, as well as academic collaborators who help to provide some of the data that we generated here, as well as the funders who, of course, we couldn't do any of this without.